Welcome back, everybody. In this unit we cover groundwater. And a big shocker, section 1, also groundwater. Now you might recall from the last unit that Earth's water is mostly tied up in the oceans, and actually only 3.5% or so is actually in either other saline waters, places like estuaries, or in freshwater form. And of that freshwater, the tiny fraction, most of it is tied up in glaciers and ice caps, solid, inaccessible ice. About a third of it is in groundwater. Some of this is accessible and some of it is not. And we'll be spending actually the whole unit on this block right here, the groundwater. The point is that this is a tiny fraction of all of Earth's water. So what is groundwater? Well, you imagine you pick a spot on the ground, you take your shovel and you start digging. And sooner or later, if you went deep enough, you would actually hit water. You would be hitting what is called the water table. Now, the water that's underground is not in there as some kind of an underground lake, or what you would be used to thinking of as a solid body. It's going to be tied up in these little holes called pores. It's in the pore spaces between sediments or between little rock fragments in the ground. Now, the actual rock body that you hit as you're digging down, the one that's saturated with water, that is going to be called an aquifer, this groundwater-bearing body of rock in the ground. And now the actual point where the water begins, this intersection, you can see here between the unsaturated zone above and the saturated zone below, this interface is called the water table. And generally, there are some exceptions, we'll see the water table goes up and down with topography. So if you have a hill, the water table goes up. If you have a valley, the water table goes down. Now, generally, the water table will follow the topography, follows the contours of the land. But sometimes it doesn't. Sometimes actually the water table is higher up than the land. And what do you get in that case? Well, you get a stream, or you get a lake. You get some standing body of water. And the surface of this is the same as where the water table would be if you were underground. Now, there's something else we have to consider here, which is that the water table moves up and down over time. If you have an intense rainstorm, lots of precipitation, the water table will rise. If you have a drought, the water table will fall. So if you were in charge of drilling a well for an area to get somebody water, you would have to make sure that the well you drill goes all the way down until it hits the water table. And ideally, you would want it to hit the year-round water table. So you would have to go even deeper than where the water table would be in whatever the dry season is where you are. And I also want to zoom in really quickly here. What is going on at the small scale? What happens when we zoom in? So we have our ground surface. We have our layer of soil, moisture, water vapor, which the soil contains in it. We have the zone of aeration. In other words, this is air that's locked in these pore spaces between the particles. And as we get down to the water table and beneath, the pore spaces are filled with water. Now, surface water and groundwater do interact with each other. For example, whenever you have a water table that rises above the surface of the land, what you get is a stream or a lake, some kind of surface body of water. Now, sometimes you can have a stream that's actually gaining water out of the aquifer, out of the ground. You would call this a gaining stream because it's gaining water. You would also have something called a losing stream. So in this case, the stream is actually giving water back to the aquifer. So if you're in a region that maybe needs this aquifer to provide water for the city, this would be a very good thing. And sometimes the water can actually flow down a considerable distance to get down to the water table from the river. Now, the ground is not the same everywhere. What does that mean? Well, we've talked about all these different layers and these different kinds of materials that you can have under the ground, and some of these are going to allow water to pass through easily, become good aquifers, and some of these are going to form impermeable layers and actually block water. And the result is a groundwater system that is just a little bit more interesting and a little bit more complicated. For example, we can look at this diagram here. Okay, this is our infiltration area. This is where rain comes down and starts to soak into the ground. We have our water table surface right here. Okay, so this is the level that the water would rise to over here if it could, but it can't because it's blocked by this impervious layer here. And the result of this impervious layer on top, this impervious layer on bottom, and this continuous rainfall is to increase the pressure in this location so much that whenever there's a crack, something like a fissure, we get a spring and the water actually forces itself up out of the ground. There's also this fact that the water table doesn't have to be completely continuous, or really the water table is not the only place that there is groundwater in the ground. For example, you can have something that's called a perched aquifer, right? It's like perched up here on a ledge and separated from the main water table. So here we have our main water table where it intersects the ground surface and is higher than the ground surface. We have our river, and over here we have our perched water table that forms a spring where it intersects with the ground surface. So if you were to actually stand here and look at it, it would look like water was just seeping out of the ground, because for whatever reason, in this case, this aquiclude, our layer that stops the water from traveling, this aquifer here, our water table, cannot move down and join the other water. Another interesting groundwater feature is the geyser. So we have this system of water underground and we have this heat source beneath it. And it's going to heat the water up so much that some of it boils and turns into steam. Well, steam takes up more space than water. It increases the pressure. You add more heat over time. It builds until it's so much that it comes exploding out of the ground and you get a geyser. So where does this intersect with the world of the practical? Well, there's a couple things that are important to know about groundwater right away when it comes to the water resources side of things. First, groundwater is very, very valuable, and it only comes back at a certain rate. It only recharges at a certain rate. So even as the population grows bigger and the economy grows and we're using more and more water, there may not necessarily be more water that is going into the groundwater system. There is also this very, very complicated fact that groundwater systems tend to be very connected to each other. So water that you take out of the ground in one place will affect all of your neighbors, and as a result, there has to be some sort of collective mechanism to protect groundwater resources, to prevent one person from taking so much that it ends up hurting everybody around them. So in the state of Arizona, this collective mechanism for protecting the groundwater, these are called active management areas. Particularly, we're looking at protecting groundwater in cities where you have the most people. There are 5 in the whole state. The biggest and most important economically is going to be the one in the Phoenix area, and these have the goal by 2025 of making sure that as much groundwater is going into the ground as we are pulling out of it. Now, I've included this just to illustrate the size and scale of the active management area in Phoenix, right? So we have Phoenix proper here, Glendale, Avondale over here, but the total amount of area is much larger, a much larger region. And why would this be? The actions of one person in any of these areas is going to affect the groundwater levels of the areas around them. That's why. So what about Avondale specifically? Where do the people of Avondale get their water? Well, as far as drinking water goes, drinking water in Avondale comes from groundwater production wells, right? Pumping water out of the groundwater. But, well, there's not enough rain necessarily to recharge, to replenish the amount that is used by the city. So where is the water going to come from to recharge the aquifer? And the idea here is to divert surface water in order to recharge these areas to let the water soak back into the ground. And about a third of this recharging water comes from the Colorado River through something called the Central Arizona Project. About a third comes from the Salt River, and about a third comes from reclaimed, refurbished water, right? Treated wastewater. So what about this Central Arizona Project? Well, I've included this just to give a visual, the scale of this project. We have water here in Lake Havasu. It is diverted. Ask a civil engineer how exactly this works. Something called an aqueduct, and it comes all the way down here through Phoenix and actually continues on all the way to Tucson, supplying surface water to the cities along the way. I also thought it would be interesting to take a look at the canal systems in Phoenix. If you've lived in the Phoenix area for any length of time, you've seen the canals. These are going to be part of that Salt River project. So we're taking water from the Salt River and delivering it to all the different municipal areas in the Phoenix area. Now, I talked a little bit before about how the city of Avondale gets some of its drinking water through the reclaimed water, the so-called refurbished water. What does that look like? Well, Avondale actually has a project called the Crystal Garden Wetlands. This is one of the sources of drinking water. The idea is that you take wastewater and instead of filtering it far away at some kind of water processing plant. Instead, you can process it through more natural means. So you take the water and you put it through a complex ecosystem which has birds, fish, plants, and other organisms which can help to filter the bad particles out of the water. And as a result, you treat the water, you get fresh drinking water, and you have these beautiful lakes for the community all at the same time. I've included some photos here. What does this actually look like on the ground? We have our ecosystem, water plants, birds, and fish, right? We can look at it from a different angle. If you lived here, you maybe would know about the project. You maybe would know that you have this nice lake next to your house, but you might have no idea that it's processing drinking water for you. Actually, if we zoom out, we can see there's a considerable area that the lakes touch here. Real estate, all of which has been made more valuable by these Crystal Garden wetlands. So let's get the details here, right? Our Crystal Garden wetlands contain about 72 acres of treatment cells. What are these treatment cells? These are our bodies of water. Water originally comes from the Salt River Project or the Central Arizona Project. You flow from cell 1 through cell 14. There's no motor, no fuel involved here. It is flowing downhill the whole time. There are a few sedimentary cells which help to filter out, the solids, the heavy materials. Most of them are going to be the planted treatment cells, which look like this, our wetland ecosystems. Now, what happens to the water once it's been through all of these treatment cells? Well, it's going to flow through an underground pipeline over west to the recharge facility for the city, over near the Aquafria River. And you have to ask the question, right, okay, this is nice, but is it practical? What kind of scale is involved? It's considerable. This one actually processes about 5 million gallons of water per day. If we zoom out a little bit, what does this actually look like? Well, these are going to be the Crystal Gardens over here. This is Thomas Road. This one is McDowell, and here's West Point High School over here. And, well, where does it actually flow? It's flowing through all of these cells, getting treated, and then it flows through an underground pipeline over west towards the Aquafria River and into the treatment facility here to be recharged and put into the groundwater system. Okay, so we know what groundwater is, we know a little bit about it. Let's talk about what happens when the groundwater goes away.